Yeah, recording started. So initially this GPU or graphics card was designed to isolate graphics computations early days, and it was for fixed purpose. And later on, this graphics processing unit is programmable and configurable. So whenever I say programmable and configurable means it is flexible kind of things. Programmable means many configurations it can take. Okay, and because it is programmable and configurable, so why not use them for general purpose if applicable? So for some kind of application. So that's where we heard the term GPGPU, general purpose computing on GPU. So that's why called GPGPU. Okay, so take some scenario. Suppose you have a machine with 16 GB RAM and 8 big cores, and on top of that, you have put a 16 GB graphics card with 10,000 tiny cores. Okay, it's very small cores, each core, but that graphics card have actually 10,000, around 10,000 cores. So, and another thing is, in this case, what happens in general? So, whatever we say memory, OS sees the memories. So, OS can see memory of this 16 GB left side, whatever we are saying, 16 GB it can see. But right side, whatever the other 16 GB, it don't see because OS will not. Here address space is different. Here address space is different. So whenever you want to do some computation on GPU, what do you need to do? You need to send data from host to card, okay, and do the computations, get back the result onto the host. So this is the standard way. But nowadays, recently people have started doing the sharing of address space also. Okay, but in general, it is not said. Okay, so whenever you write a C program and the OS will see, or the what you can say, applications will see address space in host. It will not see address space in GPU. So for that, in general, Nvidia and what I can say, AMD and Intel, whoever developed GPU, so they provide APIs to send data to GPU, do the computations and get back the code. That this put the they generally develop APIs, application programming interface. And if you look at motherboards, so we're not going into detail about this, but in general, this graphics card sit very near to the Mensa. In motherboard, there are two kind of bridges at the south bridge and north bridge. That means high speed bus and low speed bus, we can say. So north bridge, whatever we connect is with high speed bus or front side bus uses. So front side bus is connected to CPU, and lower side south bridge is what I can say, backside bus are where we connect the low end device, particularly hard drive or Ethernet or some sound, very low end device we put. Okay, so kind of things. North bridge is the fastest bridge or faster interconnect or what I can switch where you connect the high speed devices, and south bridge is actually where you connect the low speed devices. And particularly GPU means graphics card, we generally put into high speed devices. Okay, high speed means bridges. So north bridge, and this left side it's so the interconnection of PCI slots, 16 PCI slots. So left side you can see PCI slots. So these are PCI Express smaller slots. This is the bigger slots. Okay, and this one is AGP slots, advanced graphics slot. Okay, so in general bigger slots and graphics slot in general we get into North Bridge. In general we say all PCI, but based on speed and number of pins we differentiate. Okay, so we don't need to go detail, but at a very high level we say this graphics card sit on PCI slots. Okay, and if you look at GPU, so GPU versus CPU, yeah.
Sir, what is the purpose of PCI bus connected to South Bridge?
Yeah, so this is also low end PCI process. So the south bridge is what I can say low speed one, but north bridge is still high speed one. So north bridge is connected to CPU, memory, and high speed devices. Okay, still it is PCIs. Okay, in lower also it is PCI, but it is low speed one. South bridge typically it is low speed one.
And sir, where is processor in the North Bridge?
No, this one is processor. You can see the figure.
Okay,
North
CPU.
bridge processor is also connected to north bridge. So ultimately, north bridge is connected to processor.
Okay.
Excuse me, sir.
Yeah.
Sir, how is tiny core different than a bigger core? Does it mean lesser cache size?
Not only lesser cache size, but many controls also its absence.
Okay, sir.
So many control, many parameters are a number of FUs, okay, cache size and control system. Many things get smaller. Okay. So that also we have slides for that. Okay, very high level we'll see that thing. Okay, so GPU and CPU we look at. So this is left part is actually CPU. So where we have 4 core. So in this figure it is showing 4 core, and right side on a GPU where we have a lot of cores. Okay, so you can see that actually this is very tiny core, small cores. And recent examples are actually GTX. And this is Nvidia. I'm not marketing this Nvidia, but taking example. So NVIDIA GTX 3090 have 10,496 cores. That is CUDA core or tiny cores. 24 GB of RAM DDR6 RAM with 36 384 bit weight. And if you look at the current cost in Amazon or Flipkart, you can see it is around 1.3 lakh. But it is a recent good quality high end, not very high end, but a reasonably high end graphics card of current days. The GPU have 10,000 cores. So in CPU, you can see 4 to 8 or 32 core, but other side you are saying 10,000 core, almost in the similar size room. Suppose you have a means, area of suppose 10,000 square feet. In 10,000 square feet, if you make 10 rooms, then 10 room or 10 flat, then what will be size? So average you will get actually means 1,000 square feet. But if you put actually 100 rooms or 2,000 rooms, then it will be divided by that. It will be in that way. So in general, area of both CPU GPU is same. Okay, so die size is almost similar, but in one case we are putting very big core, jumbo core, so that's the number is less. And other side we are putting very tiny core, so the number is very huge. And some cases the numbers play important role. Okay, and some cases number don't play. So based on these applications. So what is GPU philosophy? So GPU philosophy is a small independent function or code executed huge number of times. Suppose a very small amount of code, okay, or functions which execute independently for huge number of times, then that kind of code can be run on GPU with smaller number of cores very efficiently because we have very embarrassingly parallel. We can see small independent function or code need to be executed huge number of times. So that is the philosophy. If some applications have this kind of things, then that is more suitable to done on GPU. So number of core are in 1,000 and small tiny cores, and cores are organized into clusters. So we can say SMX or SM. So Kepler SMX have 14 symmetric multiprocessor, and each SM have 192 cores, CUDA cores per SM, and 64 dual processing unit in a particular double precision unit, and 32 SFU. What is SFU? When SFU means it is a special functions unit or transcendental function unit, sine, cos, tan kind of things, and 32 load store unit. So this is one very simple example. Another example is RTX 2080. It has 72 SM and 4608 CUDA cores, and they have put 576 tensor core, 72 ray trace core for improving the tensor performance and ray trace performance. Okay, so this particularly tensor core used for CNN DNN computations. So an explicit memory hierarchy, programmer control, and also implicit memory hierarchy in cache. Okay, so whenever I say implicit, implicit means automatically done, and explicit means we are doing through program. Okay. And whenever we say small core and bigger core, so in general, it's bigger core. So this left side is bigger core kind of thing, and this one is with many cores. Okay, so P represent the core in this case. Okay, so they have common L2 cache. Okay, common L2 cache, L1 cache, and register file, and there are many smaller. What I can say, P means processing elements. So here, so in this case, we have a big one. This is, we can say, scalar processing element, vector processing element, but it is a very small one. So if you take Intel i3, i5, so they have scalar functional unit, that is IFU, we can say, or integer functional unit, floating point functional unit, and vector functional unit. The vector is actually 8, 16, or 24 byte vector unit we do. In in general not more than that, means 4 to 8. But here in this case, number of P is in generally more. Okay, so but here for one processor they share L1 cache, means L1 data cache, L1 instruction cache, and L2 cache. But here there are many small P's are there. Okay, this is the what we say single instruction multiple data. So in a small area, so we're putting more number of instead of functional unit, we're putting what? Core, very small core. It is a core means it have actually programmable things. Okay, so it can have their own smaller what I can say instructions and data, and it can do some processing, configurable processing. So in that way, we say it is processing elements. Is this individually it is programmable, and it can we can put mostly we generally put a SAM program on all P but different data. So this is simple core. Okay, if you look at this simple means in a streaming multiprocessor, so is a lightweight core compared to bigger core. So if you look at bigger core, so it is a very lightweight one. Okay, SFU means actually means special unit functions, and lightweight P fuse it means FMA. FMA means fused multiply and add. Okay, so multiply MAC operations particularly it do. So are you able to see this figure? So this is one SM symmetric multiprocessor. So the whole GPU have actually divided into many symmetric multiprocessor. Okay, so stream multiprocessor, and is inside one SM we have many P's. Okay, many processing elements. So processing elements, it is actually you can say it is a core. Okay.
Sir, on the left side, it's also GPU. We have multiple processing elements.
Multiple processing elements.
So how those two are different?
So these are actually organized in a core. This is organized a core. These are organized in a when simple core we can organize in this way, but in GPU we organize in this way. So in GPU we organize in a symmetric multiprocessor, and inside that we have actually many P's. So one P have many SP, we can say 32 SP or 32 P. So this is what I am showing. The left side is this can be organized in the bigger core, can be put into in this format, but in GPU we generally put in this format, right side format. You got my point?
Yes, sir.
Yeah. And ultimately, if you come to CPU and GPU layout, means how much area they use. So you can see this is the CPU where they use 4 core. Okay, 4 bigger core. So it have actually 4 ALU. Ultimately, green part actually do the computations. Green part actually do the computations. The yellow part actually brown, or we can say this part, yellow part. So this one is actually do the control part. Control part means whenever you have sequence, what I can say, processor, it have actually control part also, control part and data part, and these are actually data cache part, memory and DRAM part. But in case of GPU, so this control and data are very small one, but we have huge amount of ALUs are very small configurable P. So most of the area are utilized by smaller P as compared to the control and cache. Okay, so if you look at whole cache and control, its proportion is very small, but ALU are means what you can say actual compute unit is very huge. Huge amount of area in GPU get utilized by the compute unit. So ultimately, huge area of GPU is used or utilized by compute unit. In this case, huge area are utilized by cache and control. Okay, cache and control, not by the actual compute. Green part is the compute. Okay, so in that way, compute capability of GPU is much higher. Can you go back and see means the what is things our roofline model. In roofline model, what we studied? Roofline model. So P peak, P peak. So in GPU case, P peak is much higher. Okay, but it have more compute capability. It have more compute capability because most of the part of the means what I can say chip area is utilized by actual compute unit or green part, or in this case, or means processing part. Okay, so these are huge amount of P peak. Okay, but if you can supply or if your applications have cache kind of structures, then GPU will give you the huge benefit. Okay. So this is another Nvidia structures, whatever I shown these things. So GPU organized in this way. So there will be many SM, and inside the SM there will be many processing unit. Okay. So ultimately, what you see, if you look at Nvidia architecture, this is a little bit older one, but it have many organized in a 3-level hierarchy. So TPC is texture processor cluster. So the whole GPU have actually many TPC. Okay, many TPC. A TPC have many SM, symmetric multiprocessor, and ASM have many SP. This is SP is actually streaming multiprocessor, or what you can say, streaming processor we say. SM is streaming multiprocessor, SP is streaming processor. Okay, and many SM, okay, means many SPs they share the special function in it. Sometimes many SP, okay, streaming processor, they share common floating point in it also. Okay, they share common floating point in it. So that's why whenever you purchase any graphics card, so there are many variety of graphics card. One is actually not industrial purpose, and one is commercial purpose. So commercial means what you can say general common usage. Okay, and is industrial usage, and one is actually means high end usage. So there are 3 different means categories. General, our for desktop and common people, whatever you use. So for that, so particularly Nvidia have a GeForce series. So GFORC, GeForce series, and one is B series and P series. So they have 3 different category. So for grid or for HPC system, the graphics card are different. Where number of floating point will be more, SFU will be more. Okay. For SM, number of floating point, double precision floating point or single precision floating point will be more. So in that way, they categorize. Even if this RTX 3090 have is around 10,000 core, okay, and it is around 1 lakh. But if you go for once HPC versions, okay, or grid version of same number of processor, same number of CUDA core, then it will be much costlier. So it will be around 5 to 6 lakh because they put more SFU there or double precision unit there. And this is a very old architecture. Yeah.
You said it in GPUs the speed is bounded by PP. If that is the case, then no, sorry, the P peak is very high, so the speed is performance is bounded by memory access, right?
Yeah.
So if that is the case, then like what is the point of using GPU? Because the only benefit GPU is providing is speed wise, right, performance wise. But if we are lagging in sending data to the GPU, then how is using GPU doing any better?
Look at some applications. So some applications you can put into means actually GPU memory and do the calculations. Okay, so hold data. So you can use as an accelerator. You have capability, use as an accelerator. So suppose you put all the data there and you just calculate. Okay, so that is the way. So with some applications, we require huge amount of computations. We may not require huge amount of what I can say data.
Oh, okay.
Okay.
Where density is very high, you mean that per unit by more
Yeah,
flops? Sorry.
because it is very huge.
Okay.
So then why not to put? And another thing is we have already discussed some algorithm category. So order of n cube by order of n is there, suppose. So do you algorithm classification or application classification we have studied. Suppose n cube by n. Suppose n amount of data you need to send, but n cube computations is there. Then you will get huge amount of benefit because your means suppose your processor is capable, then you can get a huge performance. You got my point?
Yes, yes. Then GPU will be used like very highly. Okay.
Yeah, yeah. Even if it is again. Hello.
Yes, sir. Yes, sir.
So we are getting some echo.
I'll
Mute yourself. So even if you are sending means your application is order n by n, but this constant, suppose that constant is very huge. Suppose 100 n by n, 100 n by n. So suppose for each data you are doing 100 extra computations, then it is still compute dominated. So in that case also you can take benefit of GPU. So ultimately, thing is that your computations is very your application require a very high compute demand per data. Then definitely GPU will give you the benefit. So this is a very old architecture. So GTX 690 architecture. I'm showing the figure. So this is organized into two part. Okay, two device, and each device have 4 SMX, and each SMX have a very huge number of what I can say processing unit. This is a 22 SMX and 128 SP per SMX, and total is 2000 core. This is very old one, 6 GB of DDR RAM. What I'm saying is this is again little bit of 4000 core. So earlier was 2000, this is 8000, 4000 core, 72 SMS and 64 SP per SMX, and they have also 576 tensor core and 72 data trace core, 11 G of DDR. So what means this one is earlier one. GTX 980 is around 2015-16 we got this thing. This one is I think so 2018 or 19. But recent one, whatever I saw is RTX 3090 3090. That are actually recent 2021 one. Okay, so we'll get 10,000 cores. And if you look at CPU GPU performance gap, so where do we get performance? The only compatible applications, not for all applications. Okay, so this is very old slide still, 2003 to 2010 data is there, but still the concept is same. So for some applications, if the application is very compute intensive, what I am saying is compute intensive means per bytes, how much computations you need. If it is compute intensive, then GPU will give you the best performance. You got my point? If the application is compute intensive, per data, how much computation you are doing? If your per data, if your computation is very high, then GPU will give you better performance because GPU have compute capability. That P max is higher here, or what is P peak, whatever you can do, or that capability is much higher because GPU have more number of what can say functional unit or ALU, whereas CPU don't have. Okay, so that's why for some applications we can use this GPU as oscillator. Okay, programmable oscillator. So this is GPU. So given the hardware invested to the graphics, do graphics well, but how can you supplement to improve the performance of a wider range of applications? That means for some applications, so if it actually require a huge amount of computations and it is not very memory intensive, then why not to use the GPU card to improve the performance? So that philosophy comes that given the hardware invested to do graphics well, but people thought of how can supplement to improve the performance of other applications, wider range of applications, not only the graphics, but applications which is competence, more competence. So basic idea is it is a heterogeneous model. CPU is the host and GPU is the device. Okay, and develop a C-like program language for GPU and unify all the GPU parallelism as a CUDA threads, or programming model is single instruction, multiple threads. So this is Nvidia term, but non-Nvidia, particularly ATI or AMD term is they use OpenCL. Okay, Intel use OpenCL. There are many other other people they use OpenCL. Okay, OpenCL. Okay, so this is another language. So for programming GPU, but both are similar. So we saw that this hardware is organized into big devices, then GPU devices, then GPU devices are organized into SMX. Okay, TPC, then SMX, then it is SP, streaming processor. So hardware are organized into streaming multiprocessor, then streaming processor, SP. So ultimately, whenever you write software or program for GPU, so we write code in this way. Okay, thread and block. A thread is associated with these data blocks, and thread are organized into blocks. Blocks are organized into grid. And GPU hardware handle thread management, not applications or OS. So ultimately, this particularly threads are organized into blocks. That means a block get assigned to a symmetric multiprocessor. Okay, a blocks get made into a multiprocessor, symmetric multiprocessor. Okay, SMX of GPU. Okay, and a thread get mapped to a core or P of or SP of GPU. So that we will see once in the examples. So mapping of software organized to GPU. Software CUDA program or CUDA threads. Threads are organized to grids, block and threads. Grids contain block, block contain many threads. Okay. So with examples we will see, then it will be more clear. And this and hardware GPU cores are organized to cluster, which is SM. So this example is GTX 690 have 8 SM and 192 core per SMs. Okay, GTX 980 22 SM, 128 core per SM. That means in this case, the OS scheduler or the GPU scheduler inside that thing, it actually made the software block, the block content threads, block to SM, and then thread to core or SP. So block get mapped to SM and thread get mapped to SP. Very simplistic management. Okay, very simplistic management, thread management. So we don't require many complicated one. Suppose you want to create a parallel 2000 threads for applications. Then you can organize the thread into 10 blocks and each block containing 200 threads. Then we can run on top of GTX 690, suppose with 8 SM and 192 SP by SM. Then the scheduler map 10 block to 8 SM. So it takes how much time? 2 iterations into 10 by 8. So we make 2000 threads into 10 blocks and each block contain 200 threads. So this 10 blocks get mapped into 8 SM and it takes 2 iterations. Okay. And internally again, so 200 threads per block. That means 200 threads get mapped to 192 SP of SM. It takes again 200 by 192. That is 2 iterations inside the block. Block get mapped to means SM. They also take 2 iterations. The thumb rule is number of blocks should be multiple of SM and number of thread per block should be multiple of SP per SM. So that is better in organizing our high level threads. Okay. So how one, let's see one example and then it will be more clear. So this is very simplistic examples. This is a double precision. So what I say, double precisions AX plus Y. Okay, so what is what doing AX plus Y? Okay, A is a scalar and X and Y are vector. Okay, so X and Y are double vector, and this is DexP in C. So double precisions AX plus Y. Okay, so YI is equal to A into XI plus YI you are doing for N data. And clearly we can see is ith iterations. Okay, ith iteration is independent. Okay, on with I plus 1 and I minus 1, whatever to say. So ith iteration is completely independent. So these operations can be done in parallel. This is example. That's why I'm saying order and these things. Okay, very simplistic. So we may not get performance in this code, but for example case we're taking. Okay, and how we invoke the code? This is C functions, and we invoke with DexP n. So 2.0 x and y. So n is for how many data we are doing, and this is scalar value a is 2, 2.0, and 2 vectors x and y you are doing. And what will be the CUDA code or GPU code? So CUDA is popular in GPU domain, so we are going for CUDA. So in this case, this is the in host underscore host. This is signify that this variable is in host, and this is number of block we are defining. So n plus 255 by 256. This what we are saying. It is how many we are creating 256 thread per block. Okay. So in software level, so threads are organized into block. So we are creating means number of blocks. How many number of blocks? Suppose n is whatever the number, we are adding n plus 255 by 256. It's actually ceiling. Okay, so it gives a ceiling value, nothing else. Okay, so n by 256 still whatever you put, right, that also it's same as. Okay, so it will be same as a what is the second? So in this case, so this thing is actually same as nb is equal to, so n by 256 ceiling. It will give similar thing, ceiling operations. Okay, so nothing else. And this is invocations. This left, this one is invocations. And how we write the CUDA code? CUDA code is actually, this is a device because both are separate. So host is your PCs and device means your GPU card. In GPU card, these are the, this signifies these functions. It's on GPU. Okay, it can be downloaded or uploaded to GPU. So this is the XP function, same thing. And what we are trying to do, so rest of the, if you look at n, a, x and y, all are same. So what are extra thing you are getting is block id x and block dimension x and thread id x. Okay, so what, how many blocks and what is the dimension of block, and after that what is the thread ids. So we'll discuss what is I, means it signifies the what is the thread id. This I signifies what is the thread id and it can be calculated in this fashion. Okay, so this is two-dimensional, one-dimensional case. So this can be very easily, and if I is less than is equal to n, then only you calculate this thing. If I is greater than, it is going out of boundary. So this is a CUDA core for means DexP, and how this whole program looks like. Whole CUDA program for means DexP calculations. This is the block. Okay, this is the what you can say, these functions, DexP functions, CUDA DexP function, and in main functions what do we do? So in main functions, what we're trying to do is simply this part. This is declarations on the device. This is declarations and memory creations on the device. Okay, so CUDA malloc void ampersand xd size. So this is you are creating or creating data storage in the device. Device means in graphics card. This red two part. This one is declarations, and this particular CUDA mem copy. What we are trying to do? We are trying to copy data from the host X to the data to the device. Okay, so we are copying the data X data to the device. Here we are copying Y data to the device, and then how many number of block we are calculating. Then we are invoking the DexP. So this DexP functions, what it will do? This will how many block and per block how many threads. How many block and per block how many threads will be created. This is software organizations of threads and block, and this is for n data. So n is suppose you define 1024, and this is a is 2.0 and xd and yd. So here we are saying xd. So do in area of x means device storage, not the host storage, because host x and y are different as compared to device x and y. So that's why we do a underscore xd and yd. And after that, after the computations, what do? We do a reverse copy. So in this case, we copied from host to device. We copied x array to x array of device, y area of host to Y area of device. Then after computations, we compute back, means return back the result. So this is returning back the result, so nothing else. So in this way, we can write a CUDA program. So this is, if you can see this thing, this is actually distributed memory programming. Address seen by the host and address seen by the device, both are different. And we are using explicit send and receive kind of thing. So we are sending the data to the device X and Y, doing the computations, getting back the result. Means we are copying back the result from device to host. Okay, so explicitly we are doing. It is not internal. It is we are writing these things in program. Is this clear?
Sir, we are using underscore underscore device and underscore underscore host to say that this variable is
Yeah.
saved in.
In C, you will not be able to. So you need to compile this code using NVCC, means Nvidia C compiler. Then only you can compile this underscore underscore device underscore. This is actually specific to the CUDA C. This thing is specific to this annotation is specific to the CUDA C.
Okay, I mean that keyword is for saying that those two variables are created in device memory and
Yeah.
okay.
And whenever you say CUDA malloc, it will default create on the device. Okay. If you do simple malloc, it will be create on host. Okay. So there are some standard API. These are the APIs. So this CUDA malloc, you can say API, application programming interface, already created, given by the CUDA compiler. Okay, or Nvidia community.
So, sir, all the argument passed to a device function must be on the device.
Yeah.
Okay. So, like we have kept capital N.
Yeah, capital N is fine. If it is a value, there is no issue. If it is array, then it has to be in device.
Okay.
You got my point. In C also, array is not. It is what if it is suppose int xn and yn. So it is a constant pointer. Okay. It is array means constant pointer. So in this case, we need to do the pass the xd and yd, which will actually correspond to the device memory. But n and 2.0, these are values, pass by values. There is no issue for that. You got my point?
Yes, sir.
Okay. So in general, whenever we organize, so in this case, what we are organizing? So number of block is something, okay, and number of block per thread. I mean, sir, number of thread per block is 256. Okay, so this is the way how we invoke, but this can be a different type. Okay, so this invocations kernel. Suppose you are invoking a kernel with two-level thread hierarchy. Kernel app. Suppose this is a kernel app. So 4181. So what it says? This app actually. This is a grid having 4 block of 1 dimensions, 4 block of 1 dimensions. This is block 00, block 01, block 02, and block 03. So this is 4 cross 1 thread block. Okay, and each thread block having 8 cross 1. So 0, 0.0, 0, 0.1, and up to 0.7. So each thread block contains 8 cross 1 threads, and this is I block ID X and block IDX dot X. Okay, so this signifies, so what I can say, block ID and thread ID you are referring to. What block ID and thread ID you are referring to. So in that way, you can get the answer thread ID, ultimate thread ID. So because every block have thread ID. Every block have thread ID. So which block, which thread. So from that, ultimately, you will get the final thread ID. Okay, and how will this is another way of representing same thing. So this is 4181. So this can be 2242 also. So this is in each grid you have a 2 cross 2 thread block. So this is block 00, block 01, block 10, and block 11. So this is block get mapped to SM and thread get mapped to SP. Okay, SP means CUDA core. Okay, and here 4 2 means here organized into 4 into 2. So 00, 01, 02, and 03, and in this case 1011. This is each thread block content 4 by 2 threads, ultimately 8 threads. Okay, but organized in a two-dimensional fashions. Okay, so in this case, block dimension x, block ID x dot y plus block ID x we are doing, and j how we are getting block dimensions x into thread ID x y plus thread ID, just like similar to how we address or access a particular block or address a particular threads. Okay, in a two-dimensional grid kind of structure, how we access a particular element, nothing else.
Excuse me, sir.
Yeah.
Sir, is there any benefit in organizing it in this way, 2 cross 2?
No, means it may not be much beneficial, but what you can do actually, ultimately block get mapped to the SM. So it depends on how many you are doing. So this is how for our means what I can programming way, what I can say, it will be easier to visualize. To visualize easily, we can make it two-dimensional and three-dimensional block size and grid size.
Yes.
Okay, ultimately it will be converted into single dimensions. Okay, so for visualizations, easy visualizations, people go for multi-dimensional thing. Okay, and how this grid gets scheduled or things get scheduled on the graphics card. So suppose a grid having 2 cross 2 thread block. Ultimately, how many thread blocks? Ultimately, 4 thread blocks. And this 4 thread blocks. Suppose you have 3 SM in your graphics card. Suppose you have 3 SM on a graphics card. That means it will block 00, block 01, and 10 get scheduled in one go, means one iterations, and then block 11 get scheduled in another iterations. So scheduling 4 blocks on 3 SM. So this is page wise it too. In first page 3, then another page another one. It's very high level block gets scheduled into SM. And internally, so thread gets scheduled onto the P or core. Okay, suppose you have 8 threads and 8 thread gets scheduled into 8 core, means individually it will do execute on each thread get individually assigned to each core. So in this case, executed with the width of 4. Suppose there are 4 P or 4 CUDA cores in a particular SM, then it will execute it in this way. Okay, if it is a 8 CUDA core, then it will execute all together. Okay, so the threads get assigned to SP or P. Block get assigned to SM. So this is the high level thread scheduler, how it actually schedules the work. And now we'll see as what kind of applications and what kind of scenario it will be beneficial to use the oscillator or GPU as an oscillator. Suppose you have a machine configurations, Pentium quad core with quad core means any means i5 or i3 or i7 whatever. Suppose 4 GB RAM and install a GPU card with 3000 core and 4 GB RAM on GPU. Suppose you have a scenario is this kind of things. So you have a 4 GB RAM. This is a host, and you have installed a graphics card with 4 GB and 3000 core, tiny core. So this is the scenario, and needs to configure host to GPU memory data transfer and vice versa. So suppose you take vector relations, vector sum, matrix multiplications, and body simulations, image histogram. Which applications will be beneficial for what kind of purpose? Okay, or whether it is beneficial to GPU or not. Suppose you go for vector additions. Suppose in this case I am putting 1000. Okay, so it can be 10,000 also. Okay, so I is equal to 0 to n I plus plus and AI is equal to bi plus ci, parallel independent work. So whether this code, vector addition code, will be beneficial to run on GPU or not, GPU program or not. So executing a host, it will take order runtime and zero data transfer. So, and if you do on GPU, same thing, then what do you need to do? So we need to transfer 2 into 10,000 data need to send to host to GPU, execute the data in order one time in parallel. Suppose you have 1000 core, then transfer 1000 data need to be returned to the GPU to host. So ultimately, it takes 3000 unit communication over it, and it is actually not a good candidate. It's funny. This program is not candidate to run on GPU. Instead, what you can do, you can run on actually write a OpenMP program or pthread program. Divide for a jumbo core, take 4 jumbo core. Each thread can run from 250 locations. No need to data transfer, shared among all. And it will take n by 4 time. Chances is very high. OpenMP for this code vector additions, using OpenMP is better off instead of using and running on actually GPU, because you need to transfer data to n data, you need to transfer or get n data, and you can finish in order one time. Execution can be order one, but use a huge communication over it. So this application is not at all suitable for GPU accelerations. So suppose for each data you are doing a huge computations. Suppose for each data you are writing a functions which actually takes more than 100 or 200 cycles. Suppose for you are transferring something, and this is instead of AI and PI. Suppose what you are computing is what I'm writing is let me write the in pen. So instead of this AI by, what you are trying to do is AI is equal to some function of BI and CI you are doing, and this function is not a simple function. It takes suppose 200 or 300 cycles. If this function is not small function, it takes independent function, but it takes 200 or 300 cycles, or little bit of longer cycles, 15 or 20 or 100 cycles. Then still it is beneficial. Send 2n data, do 100n computations, and get n data. Are you getting a point? If it's a very simple computation, it's not worth to send to GPU. It need to be compute intensive. Okay, you got my point? Even if it is not order of n, but if it is more than, it takes 200 unit time, not the 1 unit time, but take 200 unit time, and it can be done in parallel. That is still beneficial. Okay, so suppose vector sum. Suppose you want to do vector sum. What you are doing? S is equal to S plus AI. You have only one array. Executing on host, it will take order runtime, 0 data transfer. Execute on a GPU. So suppose you are doing a vector sum. S is equal to S plus AI. So ultimately, what is this program? So this is reduction. We have already studied what is reduction. Summing up all the number into a one number. S is equal to S plus AI. And even if you get 1000 processor, suppose for 1000 data, can you do in order one time? It is not possible, because we are doing summations, reduction operations. S is equal to S plus AI. 1000 data to be added. To add 1000 data to a single target variables, so it will take at least log n time. You can make it a T format, even if you have more number of core. And one data need to be written. So this is one data need to be written. And what finally 1000 unit for communications over it, and you need to and time is, what is the total execution time is on GPU? On GPU is a log n, and on CPU it is only 1000. So 1000 data you need to send, do in suppose 8 times. Okay, 1024 and 8 times. So 1000 plus 8. So it is taking higher time if you look at. So in this way, it is also not a good guy for do oscillations. S is equal to S plus A also not good for vector sum, is also not good for GPU. But instead you can do in what I can say OpenMP and pthreads. So suppose you have 4 core, because our host is 4 core. Okay, no need to data transfer, which can share among all, and Another thing is n by 4 plus 4. Why I am putting 4? Because you to divide into 4 parts, and each processor will do individually, and then after that you collect the 4 data and sum it to final sum. So time will be n by 4 plus 4. So this will be much faster. This is good news kind of thing. So instead of using GPU, it's better to do on the host. Is this fine? Hello, student.
Yes, sir.
Yes, sir.
Sir,
Yes,
so,
sir.
sir, we are assuming that transferring a unit of data to GPU is same as doing a unit computation on CPU.
Yeah, that assumptions you are doing. That's fine.
Okay.
Let's take matrix multiplications. So this is matrix multiplication code. Okay, so and if you look at the inner loop, so how much on your host? Suppose you are doing a serial computations. Okay, so n cube time. Even if you are using Strassen method, n to the 2.8 or something time it takes. Okay, and so if you are doing on GPU, suppose you are doing on GPU, then you need to transfer 2 n square data need to be sent from host to GPU, n square data from GPU to host. So we need to send A and B, and you need to get back C. So ultimately 3n square communications you need to do. Okay, and how many computations you need to do? So suppose n square computations, suppose you can do, and suppose in this case, suppose you have 3000 core in your means GPU. Okay, so this n square computations. Okay, this n square C computations, each C computations. Okay, each C computations can be done. This internal loop, this can be done in parallel using 3000 core. This internal loop independently can be done. Suppose all the data available there. Suppose all the data available in means data means A and B are available in the host. What we are trying to do? We are trying to analyze theoretically. So ultimately, this n cube computations, all n cube computations, n square by 3000. This is whatever is C, and for each one we are doing n. Okay, so n computations. So whole n cube computations can be done in parallel using 3004 with time. How much time? Because n cube by 3000, it can be done in parallel. Maybe this tiny core may be slower, but still you can assume that suppose both are similar performance, then n cube by 3000 time. With that amount of time we can finish. That means significantly lower time we can do the computations. Significant reduction in time. In this case, it's really scale. Okay, this program is a really good candidate to run on GPU, matrix multiplications, because we require n square data need to be transferred, and computation is n cube. Okay, and you have GPU have many cores, then this is actually a very good thing. So here computation is higher as compared to communications. So this is not communication dominated, this is actually compute dominated. So this is a good program for GPU. And executing a host, so suppose n square by 4, suppose each thread can run n square by 4 CIJ computations. No need transfer, sad among all, but okay, not much reduction in time, because in GPU V2 it will be much more, reductions will be higher. Okay, so OpenMP and pthread program for matrix multiplication is not good. So that's all the CNN, DNN, they use matrix multiplication program, and most of the time for matrix multiplication, GPU perform very nicely. Is this clear?
Sir,
Yeah.
how n square by 4? It should be n cube by 4, right? Because it should be n cube by 4.
No, each thread I am saying. Oh, okay, n cube by 4. Yeah, it should be n cube by 4. No, but in that case, n square by 4 CIJ computations I wrote.
Yes, sir. And then its Cij is n. Okay.
Yeah. So whenever I say n cube computations is fine, but n square by 4 Cij, whenever I say each Cij have n computations. Are you getting my point?
Yes, sir.
Yeah. And there is another funny program that is called N-body simulations. As already time is up, but still I can say. And this is the last one. And in N-body simulations, what you would do for a large number of, suppose you want to simulate our universe or simulate atoms in a particular, what I can say, material, then they actually interact. So in that case, they simulate for longer period, infinite time, and for each element or for each body, they calculate the force. Okay, by actually getting from all other. So Fi is equal to 0, and for j is equal to 0 to n. So Fi is equal to Fi plus, they calculate the one term force, Fi j. You can say this force calculations is can be like this, G mm by r square, this force calculations. Instead of force calculations, so I'm writing G mm by r square. Okay, so and after that, what you do? You calculate the accelerations and you calculate the positions. And position and accelerations, acceleration is F by m. So how much force and what is the mass? And this is the pi. This position will be based on is the function of acceleration and previous positions. So this is actually standard code for actually n-body simulation. And whenever n is very huge, so if you look at this calculation is n square calculations. So this outer loop is n square calculations. So this is n square calculations, and this is order n calculations. Suppose the data is already in GPU, and you are getting only position only. Okay, so suppose you want to simulate the n-body simulation, then suppose put the data, initial position and initial accelerations and initial force into GPU, and every time calculate n square time, but get out the data only n time, only position you require. So n square computations and n communications. So this happens in n-body simulation, and n-body simulation is actually very good, what I can say, case for GPU. So n data sent from host to GPU. Okay, first old positions and data from old position. But sometimes you can put onto GPU, and every time you need to get the only position data. Okay, and this is actually embarrassingly parallel. Very good candidate for doing parallel. Whenever you see any GPU demo, Nvidia or AMD or Intel or any whoever GPU domain, so they give matrix multiplications and n-body simulations for. These are the candidates or benchmark to show how much performance they are getting on their GPU. And these are the two applications where accelerations work can be done very efficiently on GPU. There are many candidates. Not only this, there are many candidates. Okay. So maybe means today time is up. So if you have any questions, then you can ask.
Sir, if there are multiple type of GPU, then
Yeah.
how is the programming done? Like one is Nvidia and another is AMD. So do they support different kind of instruction set, or what is the scenario in that case?
At high level in general, OpenCL with OpenCL we can program both Nvidia and AMD GPU. Okay, but performance wise, in general, OpenCL is not good as compared to uh, Nvidia CUDA. So many places they exist, but if you go for in general, whenever they want to mix, then they generally try to do at very high level, not at lower level. In a same program, they don't utilize two GPU. Okay, so for two different programs, they utilize a separate GPU. Okay, suppose in
Okay, so
suppose in two
there
GPUs, use two separate program to write separately. So they don't actually intermix in general. It can be intermixed, but
so there
intermix.
okay, so there are many GPU intensive games. So the host machine uh, can be having Nvidia or AMD graphic cards. So
Right.
how they are managing I mean, how the game is developed in such a way that it can work properly on both of the machines.
So they support whenever someone develop a game. So they generally support a high level API. So high level API, they write on top of high level API. So if it is underlying hardware is Nvidia, so that will be translated to Nvidia. If underlying hardware is suppose AMD, then that will be translated to AMD style API.
Okay.
So just like I'm giving a very simplistic example. So whenever you write file to your hard disk or SSD, do you get any what I can say field?
No.
Or we don't get any field.
Yes.
Everything is dealt by API. Okay. So whenever you're writing file, if it is going to actually SSD, it called the SSD API, and what it is writing to hard disk, then it called the hard disk API. Nothing else. So the developer provides the API, and this developer means Nvidia and AMD developers. Particularly, they provide whenever they provide drivers, they provide the API, and the game developers they use that API.
Okay, so it is a duty of a game developer to utilize the number of cores and use them accordingly.
Yeah, number of core means utilize that APIs.
Okay.
Okay, if the underlying hardware is Nvidia, then utilize the Nvidia APIs. If it is underlying hardware is what I can say AMD, then utilize the use the AMD APIs. Automatically generates. Whenever you install a game, it configures. Configure means it inspect what kind of hardware is there, and based on that, it install the or reconfigure the game.
Okay, sir.
Okay,
Thank you, sir.
that's fine.
Yes.
Any other people have any questions?